Okay, hopefully I'm live, but I was just thinking about all the things that I did in the last stream, and I was just thinking about all the things that I used to do when I first started my Shotfire career, my journey in blasting and drawn blast, and one of those was detonator cord timing, and I was like thinking, well, how am I going to show that on any of the modern applications, because it's certainly something that people don't consider that much about anymore. However, I thought, well, somewhere in the shed is a very, very old copy of a program that was brilliant in the 90s. And so this program is now, or what is it, 20, 30, 27 years old. I think at least 27 years old. And I'm talking about this program. Yeah, it's a very old DOS-based program, and I thought I would show you very quickly. This is just a really quick live stream, I think, but a really quick look at how blasting programs used to be. Anyway, so I've done a couple of files up, and gee, it took me most of the morning to do because I didn't realize how limited these are in terms of speed and response. Anyway, but let's get one up. Let's get a file up and see if I can. It might make a liar of me, and then I will not do that. Sorry, cancel that one. I'm going to file load, and I'm going to load in these. I've got a couple of here, which are detonator cord and detonator cord 2. So I'm going to open up this one first because this is how we used to do it, or I used to do it when I very first started. Obviously the data file was different. There it is there. I will just get the zoom up, and it's it's still pretty good. I mean, I must admit, like, I'm pretty impressed with this program. Oh, here you go. Alright, so it doesn't know what the database is, so it's broken what I had done. So I guess I better go and set these ties to the correct style of tie. So well, where are we going to go here? We're going to have to remember all these things. It's been, well, like I said, 20 odd years. So yeah, data. Yes, I know. So I'm gonna say the surface. Well, I hope that hasn't been the case, where it's replaced all the downlines. But anyway, let's go with Uniflex cord, and you'll get some. Well, we need one of those, but we'll get that later. We'll get some MSCs. I called them MRCs before in the previous stream, and that's okay. That's a corporate name. MRCs, millisecond relay connector, but these are MSCs, which are millisecond connectors. And we'll get what else did I need? Oh yeah, I need a bridging det, something that people don't really think about anymore these days. And this one here is MSXL, and we'll just hit these in. Just make sure that we've got these. MSXL was a ICI range of detonators. ICI being a very British company, but they then later on turned into Orica, which was well, you can decide what you think about individual companies, but I really enjoyed the products that ICI created. They had a real customer focus. It was completely different then. They were rocker. I suppose because they came to site. Every time they came to site, they would bring gifts. Yeah, lots of gifts. So as a person in the blast crew, you've been 6 weeks on site, and someone comes along with a set of gifts. Well, that was pretty exciting. Yeah, what do we got here? I don't know what we've got. What did I put in here anyway? Oh, this was something like, so ICI made a specific range of half delays because they would sit their MS range all the way up to 200, and then they had to put in a half delay because in the normal range they jump 50 millisecond increments from 8 onwards. Well, in the normal millisecond range, but then they did this half range. You might be aware of that, but this is how we used to do things. I don't really like it. We'll just put it in 25, but it's not the right one. I think we'll just oh, there. I just saw it there. I just saw what the which is a 0 delay. There you go. Awesome. All right, so we've set that up. Okay, and it doesn't look like it's done what I wanted it to do. So we've got chord only here. I'm just wondering whether it's easier just to redraw it all for your purposes or to swap it. And I think we might do a swap, but let's draw one anyway, just to show you what it looked like. I'll draw one bridge out or one cell out. So here we go. We'll get this chord up, and I'll draw this one cell. And it was pretty simple. That's it. It's got a terrible refresh rate, but you know. But I think that could be the way I'm emulating it, because I'm running it on a Mac in an emulation mode, and you know, so it might be the delays might be all mine. I never remember it being this slow, but then again, everything was pretty slow back then. You know, 30 years ago, people's sub-millisecond response time, no one was really interested in that. I'm going to probably have to do this with the next one that I have done as well. So anyway, just showing you what that looks like. However, you know, it's got some really cool features that I thought was really good. Tie, and you can just like swap the ties, and you can say, what are we at? Non-defined 2, the second one here, and we're going to swap that with chord only. Oh, there you go. That was pretty stupid, wasn't it? Well, let's quickly tie those back in again here. But what I'm showing you here, this is a chord cell with MSCs on the zigzags of 42, and the in-hole delays are in the 25 millisecond range with a 8 millisecond bridging debt. So that then propagates it on to the next range. Now, better to, once we've done this, this was going to be quick. I was just going to do like, oh, we'll do 15 minutes and then call it quits, but it's going to take a bit longer simply because I closed the application down and had a complaint about the database. What are you going to do? Anyway, rightio. So I've got this. Let me just check the nominal times. Sorry, the in-hole delays. Let's see what we've got as in-holes. So the in-holes have stayed. So that's really cool. I've just turned on the in-holes and they've stayed. You might not be able to see it, but let's just get the window up and zoom in a bit more. And we're going to close in a little bit more. And you can see here I've got 25s zigzagging all the way up. So you'd get down on the bench, you'd run 25s up. Well, you probably wouldn't do that because you would start off on like number 4 or something like that. Because if you started off on a number 4, it meant you had, if you had infill holes on this side, you could chuck in a 3 or a 2 or a 1, depending on how many infill holes you've got in that row. Anyway, besides the point. We've done that, so let's just get this. I was just trying to be quick. Terribly want to be quick about these things because I don't want to bore anyone. However, I just thought this was so cool. Like, who thought that you know, not much has, I must admit, not much has changed in the time that we've progressed. You know, the face of the application may have changed, but in fact the actual application's usage is not. So I just wanted to show you this. This is a zigzag cell. Bridging debts are an number 8, or not a number 8 star, a number 8 as in 200 milliseconds. There's a bridging debt, and we start with a 25. So that means that this hole with a 200 millisecond bridging debt and cord going off instantaneously, that'll be 825 downhole time. And this one over here, well, sorry, that'll be, sorry, not 825, what an idiot. It'll be 225. This one behind me is 200. Okay, so we can turn off the, let's turn on the nominal times. A little bit difficult, but you'll see what I mean there. Very crowded. Let's zoom in into this section here, and we'll see what we've got here. So we're at the bridging debts. We're going along. Here's the surface time at the top, which is 0. It's firing at 0, and it's got a 42 millisecond MSC in here, which means that this row is firing all at 42, but down the hole it's ticking away. So this one's going 75, 100, 125, 150, 175, 200, and then we have this bridging debt. We've got a few of those, because one thing you want to do with cord and detonators and downholes is have 2 entry paths for any of your timing. Cord is renowned for cutting itself off. It's such a violent, such a violent method of surface delaying. But you know, if you, each one of these knots, if they're not tied in correctly or they're too close or whatever, anyway. So you'd tie off a little tail on this of detonating cord around here, and then you'd J-clip your 200 millisecond in to restart your cell timing. Anyway, I think it's really cool. Rightio. So let's just zoom back out, and let's see what it looks like when it times. And sorry, just someone tried to call me then. Should turn it off. Radio, yeah, and then we will turn off the nominal times. Right, now we can see the layout of the pattern, and we're going to fire it. We're going to do the visualize, and you'll see what I'm doing. This is just detonating cord on the surface. So we'll do, let's do medium. So you can see those row by row firings there, and then the downhole delays are ticking away in the hole, and they fire. Now, there's a big risk here because the burn front fluctuates quite significantly. So if you think about it, the burn rate at this point is quite high. You know, it's 200 milliseconds. Or at the end of the row, the burn rate is sitting there ticking, even though the surface is fired. But downhole, it's got 200 milliseconds it's ticking, but over here it's only 25 milliseconds it's ticking. So anyway, that's quite interesting. But you can see that row by row, that's how we used to do it in the early 90s, mid 90s in gold mines. We'd just run these big long runs of cord, come along and snip them, do a little reef knot, come around this corner, and then zigzag up here. Now, what I didn't realize at the time when I was doing this was the relief pattern, and I didn't realize at the time how disgusting the relief is. So on these kinds of, let me just, so you see it's just thinking about it, but here you can see this fluctuation. You've got like 14 through here, and then you got 22 through the yellow, so you've got this massive, and that's because you're going on a zag or a zig, whichever way you want to talk about it. You're going back with your time because you go up a hole, down across a hole, sort of like this. You know, you zigzag up through the pattern. So one way to get, so what we now know, obviously, a lot of people know, is that zigzags aren't consistent in their burden relief. So anyway, how we'll save that. Little old DOS window. It's so simple. You're in this program and you're in DOS, and it's great. I thought it was fantastic. So I'm going to load up this second one that I did here. Yeah, I'm going to do that. Yep, accept. Sorry, don't know what I'm doing. And we have a similar problem with the products that are on there. See there, but I'm not going to fiddle around changing, but you can see there's one significantly difference. What I've done is, instead of running 25 up this zigzag through here, I have decided to run 25, then 50s, then 75s through here. And so what we'll do to do that is we will turn off the ties, and I will show the in-hole delays. Terrible. Let me just get that zoom fixed. That was not what I wanted to do. Alright, you can see here I've now run 25s, 50s, 75s, and you can see I replicate that. Once I get to 200, that's one cell, and then we hit 25s, 50s, 75. So they're all downholes. So all your timing is done at priming point. You do a lot of the timing at priming point. You decide on what your cells are and where you're going to walk with it, and you may, like if you're having infill holes, you would you'd have to plan those out. You'd have to pick whether those infill holes are going to belong to the left hole or the right hole or the next cell. So kind of exciting, you were actually shot firing on the bench, and you were actually doing this timing methodology in your mind. So you never even used a computer for this. But anyway, let's turn on these ties. Let's just edit that, and we will change them, and we're going to swap the non-defined number 2 for the chord only. So let's change, and we're going to change the ties. We're going to swap, and we're going to swap 1, 2, the non-defined at number 2 for chord only. Alright, cool, excellent, done. Get that overview up, and we're going to zoom. Now, I keep messing this zoom up. As you can see, the zoom is terrible. This is going to get tiresome for everybody watching. Anyway, I'm nearly done with it all. I just thought, how cool is this old program that everybody used to do? Everyone used to use this application. So now we have the ties. We got these bridging debts. This is one chord cell. This is another chord cell. This is another chord cell, and then I had one random hole out the back. Well, it's not random, depends on what you do, but essentially this is what it is. And now let's just exit that data, and let's show the calculations. Let's do the calculations. Let's visualize. You'll see medium. Let's go slow just so you can see it. There's one row, and now we fire. So our burn rate's like 2 rows, not even 2 rows. It's terrible. And what was the outcome of having a burn rate so tight on those sorts of things? Well, it was misfires, wasn't it? And as you can see, chord, if you cut this off, this was a terrible experience trying to remediate blasts that had cut-offs, and terrible scenarios. And these holes are firing and sending fly rock before the chord behind them's even fired. So you're seeing here that the surface hasn't even gone on some of these things. There we go. Let's fire that a little bit quicker. Let's do it a bit medium so you can see what it's doing. And that looks a bit better, doesn't it? I just think, like, this is like 30 years old, this program, and it's like cranking. It was This edition was done in 1993, but I only ever started using it in, I think, 95, 96. So, I mean, wow. I just think it's awesome that not much has changed in terms of the methodology and the thinking processes. But what I wanted to show you was it was called MSC delay timings. Now, I'm not sure if they've taken it out of the Shopfires course. When I did the Shopfires course refresher 2 years ago, I think there was some questions about MSCs in there. Anyway, let's have a look at the contours. And this is hell smooth. You can see how smooth these lines are. This is exactly what you get with your echelon timing, with your what you would expect with a 25 millisecond increment across the spacing and a 42 going back through the burdens. This is exactly the same. So the concept hasn't changed. It's just the tool that you're using to implement the concept. I'm going to save that. Yeah, save that. Sure. And I'm going to load that other one in because I want to, like the original one, and I want to show you this terrible zoom. All right, and I wanted to show you the difference in the angle of initiations. You know, because these angle of initiations that you see in this one, you can see this is what a zigzag does. That's what relief's doing. It's doing this sort of like bendy. It creates a distortion in the wave because there's a speed up, a slow down, a speed up, a slow down, a speed up, a slow down. Every time you go on the reverse echelon, you're slowing it down. Every time you come on the other, you're speeding it up. So slowing down, speeding up, slowing down, and as a result, you get this wavy contour line, something to be aware of. I think something to be aware of anyway. But gee, I just think this is an awesome program. Before I do that, actually cancel that. Let's do the calculations on. Yes, I know. First movements. So we get first movements. So we get little arrows. Now this is in 1993. So, I mean, we thought this was brilliant. Not much has changed. Not much has changed at all. I think essentially the core of most programs. But you can see how these arrows are all different ways. Let's see if we can zoom in just a little bit. So you can see here we're quite tight now. We can see these first movements. You can see some of the arrows are going this way, and some of the arrows are going down this way. And that is these arrows are pulling it one way. These MSCs are pulling it another way. I thought, awesome. Let's load in the other one that I had, which is the better way, the more consistent firing, and show you our zoom, and we'll also look at the relief on that. And as you'll notice with the relief on this, when it thinks about it, see how much more consistent the relief is. There's a little bit of stuff going on in here. I'm not sure why that is. Maybe an artifact of the timing, but on the whole, the pattern is moving consistently. Now that's what you want. If you're looking for ore dilution returns, you want to move the dirt consistently. If you're going to start throwing your dirt around in different parts of the blast, so that you essentially won't find the dirt. You won't find the ore. Yeah. As well as if you consistently move it. If you consistently move it, you consistently charge it, the rock mass is consistent, you should consistently get the same returns in your ore. But if you're going to fluctuate your energy in a blast hole, and you're going to fluctuate your timing, like we did with a zigzag or something like that, you're going to see additional dilution. Wow, I'm just blown away by this this tool. I mean, it's seriously awesome. And it, you know, it's like I said, it's what is it? 1993. 27 years old. Not even, maybe 20, 26. Terrible at maths. I'm good with a calculator, which is important. But I thought, well, this is what blasting used to be. We used to do with blasting, and I mean it's really good. I mean, if we clear this plan and decide that we're going to add a pattern. Let's add a pattern. Right, and 10, maybe we'll just do 5, and we'll do 10, so it's not so big. We'll keep all the rest the same. Let's put this in-hole delay to something a bit more aggressive. Well, we've only listed our database out, but had we had a number 20, it would have been about, or you know, 400. Well, that would have been 500. So I think we're around 16 or a 14. A 14, I think, was a 400 because these go 50 range. Anyway, we'll put them in at 200. That'll give us a better burn from. I'll accept that. And then here we are. We got our little pattern, and we can do it square or on an angle or whatever. Anyway, let's see what we do there. Well, let's add another pattern as well. You know, do the same thing, except and we'll let's say we'll bend it around the bench. Yeah, let's bend it around the bench like that. See, someone's gone and designed it like that. And then we'll come in here and we'll zoom in to this area. We'll get rid of some of this mess up. We'll remove holes, and maybe we should, before we remove holes, single hole, let's just show the collision. Sure, there is a maybe 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 in those days we didn't care about hole IDs. Yeah, I don't know. I can't seem to see them. How silly. All right, so let's just remove a hole, single hole, and we'll just come along here and I think we're gonna remove that hole, and then that's a normal hole, so we'll move these ones out the way, this one here, and then come around this bend. So we'll get rid of that one, we'll keep that one. Oh, look at that, deleted one there. So then I look at is really rough because we're going to change a holder, or are we going to move holes, or are we going to I thought you could. Let's try this change hole data. One hole. We'll try that. Actually, let's not do that. Let's just add a hole. Sure, I'm happy with that. I'm going to put one in here to mitigate that bend around there. Rightio. And window overview. So we got our little pattern here. Get our zoom up. It's a terrible looking pattern, you know, great design, hey. Obviously, I mean, I'm just quickly jigging it together, but you know, then we could go and pick out some delays. What do we usually do? Let's do 25 or 17s, 42s, because everyone loves to say, oh, you should have used 25s and 17s, or 42s and 17s. So we'll drop a surface product in there. We'll use a connected edge, and we'll go with a 17 and a 42. Radio. We don't need any of that. Exit that data. Radio. Here's our 17s, 42s. Doesn't really look right. You'd probably put them on this end if you're actually going to do this on this program. I doubt that anyone in the world is going to be using this program to do anything. So let's add a tie, and we're going to go with our 17. Radio. Then we're going to bend our shot down here. Cool. And then we're going to hit our 42s. I mean, I'm dumbfounded because some of the recent applications that I have tested in mining, like new applications that people would test out or say, oh, we got this great application, would you like to try it out? And you'll test it, and for some reason it's this atrocious mess that doesn't really work very well, and then they need to go and do a whole lot of work on it that to make the timing work and functional. This thing was done by, God knows, it could only be done by 2 or 3 people or something, and I mean, it's just amazingly quick considering how old the technology is, and I mean, this is not good, right? Because I'm not tying in very well. Remove a tie, a single tie. There you go, and I'll put this tie back in the right way. But I mean, it's obviously wrong. I mean, it's the wrong timing. We needed an extra few ties there, some 9s to do infill holes or something. Oh my goodness, I'm getting worse and worse. Single tie. Anyway, my intent was not to do this, but as you can see, wow, what a pretty cool little old program. And I thought I found it there, and I just wanted to show people what the world was like when I started in Drill and Blast. This was the best program, you know, in the world. And you know what, this is terribly going to create some terrible problems in this corner. I mean, it's just disgusting. But let's see. There's going to be lots of holes firing at the same time, and we will add a lead in. But seriously, this is like, let's show the contours. Let's show, or exit here and calculations and angle of initiation. Yeah, I know. Yeah, and you can see right away it's not too bad at the start, but once it gets later, we need to slow these down so that we pull these contours forward. Actually, let's just try and do it, and let's try to just get the contours straight. But we can, you know, something that people just always, well, don't always, but they never really. I mean, this is not good practice. We've only got 2 delays, and we'll just drop those in there, and we'll see what effect that has had on the contours. I'm not suggesting you do this, so please, or actually have a go at me in the comments, because any comment's better than no comment. Really need to put another 42 there, and then it will look pretty good. But you can see here how much tighter these contours at the back are. That's because the shot has had to slow down to compensate for this elongated bend at the back. And this is what I was trying to explain before about time. You know, people obviously don't consider time as a factor of importance in their timing, but it's literally the definition of the word. So exit contours. What do we do? What do we do? Well, that's all right. I'd pass that. If I was a nobody mine manager who didn't know anything about blasting and just recently been put into that role, I think I would sign that off because it looks reasonable, doesn't it? I mean, it's actually really terrible. So I wouldn't sign that off if I knew what was good for me. But you can see how powerful these sorts of these applications were. I mean, they were cranking. I mean, they're pretty simple. I mean, pretty simple application on DOS. It's like fit on a 3.5-inch floppy disk, you know, the little hard case ones. And it drove an industry to excel in blasting and to improve their blasting for years and years. And not much has changed between this product and modern timing programs. However, great little nostalgic trip back 20 odd years to look at an old program, an old DOS-based blast timing program. And I thought I would show you what happens with chord cell firing and bridging debts. And I think it's a skill you should be aware of and be cognizant of as a shot firer and as an engineer, because the premises that underlie the methods of what you do today, these concepts that underlie those methods that you use today are valid, important, and should be given respect. They show you where the past has come from and our evolution into modern timing. And man, entire industries were built, masses, roads were built, you know, everything was built because we were able to do something as human beings. I think it's really, really important to recognize how powerful the human condition is. And this it surprises me that we've come so far yet haven't come far enough. Well, anyway, I hope you like this little trip down the nostalgia lane, and if you like these videos, please leave a comment, maybe subscribe to the channel. The more subscriptions I get, the more interested I am in doing it. Like today, I really didn't want to do this live stream, even a short one, and you know, quite disheartened with the state of affairs of the world. But I thought, you know, there's people that appreciate it. I got a few messages from some people, and they said they appreciated the videos. They said keep going with them, and so that drove me on. So please subscribe, like, share. Not enough blasting videos about engineering concepts are out there, so please share them around. Let your friends know if they're engineers. Let them know. I really want to give back to the community of blasting, and I want to find some use for my time. Okay, please. Thank you very much.